suppose you were a pilot and you wanted to travel from this point to this point. What do you think the shortest path you would want to travel would be? Assuming you just want to travel continuously and like no breaks in between or something.
It is a curved path.
Okay, like which one? Do you think it's one, uh, two, or three, or something else
Can
altogether?
you tell Earth's bend? Like Earth rotates at how much degree?
I mean, I'm not sure about the exact numbers, but like just as an estimate, what do you think?
I guess three.
Three. Okay. So turns out the actual shortest path is going all the way above here and from Greenland returning to the US. Like normally you would expect it to be this straight line, but due to the curvature of the Earth, you know, it does not represent a straight line on the map. So it makes more sense when you, sorry, it makes more sense when you look at the Earth as a sphere. So for example, this is the straight line path, you know, the one, this one also. So the one passing through Iraq and stuff. This would be the straight line path. Like looking from this angle, it makes sense that this is the shortest path. So so I'll formally define what the shortest path is. One second. So basically, if you have 2 points A and B on a sphere, right, and we look at the plane AOB, this intersects the sphere at a circle, right? Since a plane and a sphere always intersect at a circle. So the intersection of this thing forms the shortest distance path. This is called a great circle. So yeah, so basically what we'll do in spherical geometry is we'll look at points on a plane, and but we'll redefine how the distances and angles and everything else is. So for example, we'll be talking about distances in terms of this arc length, not in terms of the straight line distance, which you would expect in normal 3D geometry. So, yeah. And okay, so basically, there are two ways of doing spherical geometry. You can either do them by just defining things on a sphere, or you can take the axiomatic approach like Euclidean geometry and define axioms and prove basic theorems using that. I'll be sticking to the first approach since using the axiomatic approach, you'll have to prove very basic theorems and it is not that interesting. Okay, so some things I'll be assuming is the radius of the sphere is 1. Since everything is up to scaling, it does not matter what the exact radius of the sphere is. Um, and also, just a small definition. So, if you have a point A, just a second. Okay. If you have a point A, suppose here, its antipode is defined to be the diametrically opposite point. So, the line AO, where the line AO meets the sphere for the second time, it is defined as the antipode. So, for example, the south pole is the antipode of the north pole since they are diametrically opposite to each other. And also about a lens on a sphere. Mhm. Let's see here. Yeah. So, whenever we talk about lengths on a sphere, we do not refer to the straight line length. Instead, we refer to the arc length, which from basic 2D geometry is nothing but r into theta, where theta is equal to angle AOB. But since we take the radius to be 1, we can just take the arc length AB to be the angle AOB. Is this clear? Okay, I'm assuming it is. And okay, so these are basically the line segments of spherical geometry. So whatever normal line segments you would have in Euclidean geometry, this is the spherical analog of it. And obviously we have the line in spherical geometry, which is the entire circle, uh, defined by the segment. So yeah, so angle between two lines. So suppose we had these two lines, this line and this line, suppose, right? So we define the angle between two lines to be the oops, to be the angle between the tangents at the point of intersection. So for example, let AB be a line and CD be another line. And if we take F to be their point of intersection, then we draw tangents from F to AB and F to CD. The angle between these two lines is the spherical angle between them. So for example, this angle is 44.53 degrees. We say the angle between line AB and line CD is 44.53 degrees. Are the definitions clear?
Yes.
Yeah, thank you. So, um, yeah. So, as I said, there are two ways to think about lines in general. So, one is you can think of it as a circle. So, one second. Yeah. So, you can think of it as a circle. So, like this is a circle, but you can also think about it in terms of planes. So, if I consider the plane A or B, right? So, the circle is the intersection of A or B and the sphere itself. This definition is useful because planes are nice to prove some basic properties. So, okay, you people are aware of Euclid's axioms, right? So the thing about um, spherical geometry, really sorry, my screen just a second. My screen is not working for some reason. Okay? Yes, it is. It's fine. Sorry about that. Um, is there reason or something? Anyways, so yeah, as I was saying, that spherical geometry is also called as a non-Euclidean geometry because it does not satisfy the Euclid's axioms. So hence it is like distinct from the Euclidean geometry. So so
I think you got stuck there. Did you get stuck again, or is it just me?
Sorry once again, my internet died once again. Uh, Can you people see the screen?
Yeah.
Yes.
Yeah. Right. So, as I was saying, so these were slightly rephrased Euclid's axioms. So, like, first one is like a unique line segment can be drawn joining any 2 points. Again, a line segment in the context of spherical geometry is an arc, right? So, do you think this is true in spherical geometry? That if I take 2 points on a sphere, there's a unique arc joining them.
Yeah.
Right. Just a second. Where is this not?
But many arcs can be made joining them, but a spherical arc is one only.
Yeah, a spherical arc is just an arc uh, with like this with the circle with this center as the center of the sphere.
We can consider the plane, I guess.
Right, exactly. So we can just take the plane mm, A or B and consider their intersection. So the arc is unique. But what if these 3 points are collinear? What would happen then? So just a second. If I took, let's say, a point A and its antipode, these 3 points will become collinear. So there is no unique plane passing through them.
Uh, there is infinitely many.
Exactly.
Like we
So
can consider many spherical arcs.
yeah, exactly. So there is no unique spherical arc passing through these. So it's no longer unique. So this does not hold in spherical geometry. This one holds in spherical geometry. Do you see why? If I have um, if I have a segment AB, and if I simply consider the circle which it is part of, it extends to form a line. So, uh, so the axiom holds here. What do you think about the third one? So,
It becomes less recursive. This.
sorry.
It does not make some sense here. Because
Okay, if forgot to define one more thing. You can define circles in a spherical geometry as the intersection of a plane not passing through the center. So, for example, if I take these 3 points and if I consider the plane passing through those, and if I take the intersection, right, they'll form a small circle, which we take to be the circle in the spherical
it
geometry.
can be a conic, like ellipse or something.
No, a plane always intersects a sphere and a circle. You can prove that. Anyway, so basically, this does not hold due to almost the same reason as the first one. If you take two antipodes, then you cannot construct a, you know, circle using that as the radius. Since you'll have points which are not on this sphere, which is not allowed. Fourth one is obviously true as well. And yeah, for the fifth one, which is the parallel postulate, what do you think? Does it hold in here? Basically, one second. I want two lines which do not intersect, and I want to show they are unique. That is the a rephrased version of the Euclid's fifth axiom. So what happens is if I take any two lines, right, they always intersect at 2 points which are antipodal points. Can you try to prove that for 2 minutes?
Maybe because there exist four spherical arcs for the both the antipodes.
Can you repeat? Sorry.
Maybe because there exist four spherical arcs for the antipodes.
There exists infinitely many spherical arcs to the
Yes, but
antipodes, right?
we have proved that there is not a unique one, so it makes sense they have to be one.
Yeah, but how do you prove it? Because you want to prove in the opposite direction, right? You want to show that any two lines intersect at two antipodal points. Right, so I'll just give a sketch. So basically, consider the planes OCD and OAB. The intersection of two planes is a line, right? So it is a line passing through O, since both the planes pass through O by definition. So the resulting line will be a straight line passing through O. Now, since those two, like the intersection of the two circles will be the intersection of the two planes on the sphere, and since that line passes through 2 points on the sphere, uh, they always intersect at 2 points and they are antipodal because they are collinear with O. Is this clear?
Yeah,
Right. So basically, using planes instead of circles is generally useful for proving these types of statements. Okay. Okay. Also, I forgot to mention. So for the first axiom, it is almost true. For the remaining, what do you say, non-antipodal points, there'll always exist a line segment, as the proof has given that consider the plane A or B, and the intersection will be a circle. Okay. So as with normal geometry, we'll talk about triangles now. Except these are spherical triangles, so they're points in a sphere, and they are spherical segments, so arcs basically. Right. So in just normal geometry, what do you think is the basic property of a triangle?
Okay, so the sum is greater than 180.
Sum of angles is?
It's greater than 180.
No, I'm talking about Euclidean geometry first. In Euclidean geometry, you have sum of angles is equal to 180, right? So a plus b plus c equals 180. And does anyone know a proof of this?
consider line going parallel through a B3.
Yeah, right. So then you get this angle equals this angle and this angle equals this angle. Does this same proof work in spherical geometry?
No,
Why?
because the parallel lines meet at a point.
Yeah, exactly. So we cannot use the same proof for spherical geometry. In fact, the result isn't even true. You in fact have that a plus b plus c is greater than 180 or pi r, right? Always. And even more surprisingly, the
It is shorter than 3 pi.
hmm?
It is shorter than 3 pi, I guess.
Yeah, it is smaller than 3 pi as well. But yeah, the somewhat surprising result is that if you take the difference between this a plus b plus c minus pi, you get the area of this spherical triangle. Right. So how do we prove this? So for this, we'll use one small lemma. Okay, before that, I'll introduce a term. So basically, if we take,
Because the a plus b plus c denotes the angle.
yeah, angle A plus angle B, this is the spherical angle. So the angle between the tangents and things. Right. So yeah, so this is called a loom, this area. You can think of it as an orange slice if you want, or you can think of it as a two-dimensional polygon, sorry, two-sided polygon, which isn't true in Euclidean geometry, but you can find it in spherical geometry. So it is basically if I have two lines, and so the basically the region bounded by the two lines is called a loom. Okay. So the angle of a loom is the angle formed by the two lines. So the angle by the tangents to these two lines. Right. So what the main idea is that the area of a loom is 2 times alpha. So twice the angle of the uh, loom. If you're wondering why this isn't homogeneous, so like area is meter square, but this is dimensionless, it's because we have assumed r equals 1. So for a general r, we would have 2 alpha r square, which should work. But since we're taking r equals 1, which makes things easier, we can just show that area of loom is 2 alpha. So basically what we can do is, if you're willing to assume that area is proportional to angle, okay, that's weird. Then you'd have uh, simply area by 4 pi, which is the area of sphere, right, equals the angle by 2 pi. And you would get the result immediately. But to rigorously prove it, what we can do is we can split. Um, okay. So basically, the idea of finding areas of these weird quantities is we split a known area into some quantities which are easy to compute, and then use limiting arguments to compute for everything else. So basically, what we do is we take a ln of angle 2 pi by k for some integer k. So for example, for k equals 4, we split this sphere into 4 equal halves. So like this, these half, and sorry, 4 equal quarters. So you'd have equal loans. So they'd have equal areas, right? So, and this would be 90. So you'd have area of the loon is also equal to area of sphere by 4, which would be pi. So in general, you can show that for alpha equals 2 pi by k, you have area equals 4 pi by k. Does this make sense, the splitting thing?
How do you define the area of a loom? Like, just the front part or both the parts? Like, if you rotate the sphere.
It is only the front part. This is the like a loom. So
Right.
these are not counted, but when we split them, they split equally. So the angles are equal, which is pi by 2, and the areas also get split evenly. So the area becomes 4 pi by 4, which is pi. So for ln of angle pi by 2, we have area is pi.
Right.
Right. So Similarly, for 4 is just a random number. You can split it into 10 pieces and you'd get the same result. So we have shown this for 2 pi by k where k is an integer. Now next what we can do is we can show it for p by q times 2 pi, which is similar. It's since it's p times 2 pi by q, instead of picking one piece, we can pick p pieces. And since the areas get split evenly, this also has 2 times, p 2 pi by q. Right. Um, so what we can do is, so we have shown this for p by q times 2 pi. So all the angles for these. Now what we have to show is, so we have to show it for general 2 pi x, right? Where x can be any real number. Okay, positive real number. So what we can do is we can use limiting arguments. So you can skip this part if you don't understand limits well or something. But let Qn approach R, where Q is a sequence of rational numbers and R is some irrational number. Okay. Right. So let Qn be a sequence of rational numbers which converge to R. So since the area is continuous, you would have 2 pi Qn also converges to 2 pi R, of course. Um, so the area of this angle would converge to area of this thing. So you have to find where this sequence converges. So we want limit of area of 2 pi Qn, which is nothing but limit of, from what we found out, 4 pi Qn, which is equal to 4 pi limit of Qn, which is equal to 4 pi R, is equal to 2 times the angle which you wanted. So basically, ignoring the formalisms, it's basically you show it by splitting evenly for 2 pi times rational values, and then you use limiting arguments to show it for irrational values as well. Okay, so hopefully you're convinced that the area of Lune is 2 alpha. Did you understand the proof?
Yeah.
Right. So, uh, so coming back to the area of a triangle, I think you can try to show the area of triangle for 2 minutes by using, given the area of Lune formula. Try it for 2 minutes. Right. Any ideas? There's a hint on the screen.
I think work
Can do.
backwards.
Hmm?
Um, just write the formula and then multiply by 2.
Which formula?
Um, area equal to a plus b plus c minus pi.
Okay.
Multiply by 2 so that you can get a 2 pi term.
This is what we want to prove, right?
Yeah, so you're working, I'm working backwards, hopefully.
Oh, fine.
Can I tell?
Yeah, sure.
So I generalize this to we have 2a plus 2 plus 2c is just the sum of all the three units.
Right.
Yeah,
So,
and 2 pi will be the like if there is some triangle ABC,
okay.
and you can see there exists some triangle FED which is opposite to it and it has equal area. So it
Yeah, the
makes sense that
antipodal triangle.
yeah, antipodal triangle. So the triangle CET is also having equal area to triangle AEF.
Correct.
Then we can, I guess, then we will have some equations.
Yeah. So basically, the
Then we
main idea
will,
is
yes, then we
continue.
will try to prove it that the remaining residual area sums up to 2 pi.
Yeah, correct. So the main idea is double counting. You can do that in many ways. So you can consider the area of all units and then remove the extra portion. Or you can do what I'm going to do, which is consider the area of the hemisphere. So basically, it consists of the red region, blue region, green region, and the orange region. So the red region is nothing but the area of ABC. The blue region is nothing but uh, angle formed by the lune C, right? So area formed by the lune C minus triangle ABC. And as you mentioned that the area of triangle DEF equals area of triangle ABC. So the green area, which is the lune made by the angle A, is nothing but um, area of angle A minus area of DEF, which is nothing but ABC. Right. And then similar, the orange arc is nothing but area of B minus ABC. All of this sums up to the area of the hemisphere, which is 2 pi. Once you expand all this, you get 2C plus 2A plus 2B minus 2ABC equals 2 pi, which after just dividing by 2, you get the result. Did you get the double counting? There are many other ways to double count as well. For example, you
Yeah,
can
I
consider,
got it.
yeah, you can consider all the loans A and then B and then C, and then remove the extra portion and then equate it to the area of the sphere, which is 4 pi. You'll get the same result.
Yes.
Right. So, right. So now I'll be proving Euler's polyhedron formula. You might have heard of it. It is basically given a convex polyhedron where with V as vertices, with E edges, and F faces. Right. You have V plus F minus E equals 2. This holds for all convex polyhedron. So for example, for a cube, you have 8 vertices and 6 faces and 12 edges, which is nothing but 14 minus 12, which is 2. Uh, yeah. Okay, so before proving that, I'll prove the area of a general spherical. Um, 1 second. Yeah. So area of a general. We managed to prove it for a triangle. Now let's try to prove it for any convex. Sorry, any polygon, spherical polygon. So let's take A, B, C, and D, and we want to find the area of this region, the inside region. So area of A, B, C, D. How do you think we would be able to do that?
Can dissect it into
Yeah, you can just split it into triangles. So you can just join AC, and so area is this is nothing but area of ABC plus area of ACD, which is nothing but angle ABC plus angle AB, sorry, CB, sorry, CAB plus angle ACB, and then similarly angle ADC plus angle DCA plus angle DAC, and then you subtract pi, you have pi here. So after adding all of this, you get nothing but angle A plus angle B plus angle C plus angle D minus 2 pi is the area.
So angle BAC plus angle CAD is equal to angle BAD.
Yeah, exactly. So angle DAC plus angle CAB is uh, angle A in the quadrilateral, and similarly other angles will add up.
How do you
Uh,
prove it?
yeah, I
we
mean,
can consider the tangents and we just generalize it to proving on a plane generated.
oh, yeah, you can do that, but in like 1 second, where is that? Yeah. So you have this right. Okay. Okay, that's fair. 1 second. Where's it? Hmm? Oh yeah, right. Sorry. So if you have the tangents here, oops, what is this? All right. So the angle between the tangents add up normally, right?
They're all coplanar, right? All the tangents.
Oh yeah, good point.
Are they coplanar?
Yeah, because they'll all lie on the plane tangent to the sphere.
Oh yeah, then it
Oh
works.
yeah,
Yeah.
Then
Yeah.
it holds due to plane geometry.
Now I understand.
yeah. So since they're on the same plane, the angles add up normally, and it works the same way. Right. So in general, what you can say is that uh, area of n-gon is just the
It is I
yes. So this is what you would expect in a like this is the sum of angles. What you would expect in a normal n-gon in Euclidean geometry. So this is like the kind of like the actual angle minus the expected angle in Euclidean geometry, which is kind of interesting. Anyway, so okay, so now we know. Okay, is the idea clear how we got this? You can induct from just the same idea. You just split it into triangles and add up all the areas of the triangles, and you get the area of the thing. Right. So using that, we'll be proving Euler's formula. Okay, so basically what we do is, I have chosen a cube for demonstration purposes, but this works for any polyhedron. So what I'll consider is, suppose E is a point inside or outside. I draw the ray from the center to E and mark the point of intersection of the ray and the sphere. I'll be calling that as a projection of the point on the sphere. Okay. So what I'll do is, so you can imagine it as like a light source in the on the center. The images of the cube on the sphere will be what its projection is. So okay, so what I'll do is I'll project the entire cube onto a sphere, and we'll get a bunch of spherical polygons, and we'll use double counting to uh, compute the area of the polygons. So okay, so initially the area of the sphere is nothing but 4 pi, right? And you can also write this using the polygons as the summation over all polygons of the area of polygon. So these,
Each of the cube uh, projects a convex, convex quadrilateral on the sphere.
yes, you can assume that, I think. Yeah, I'm pretty sure. Okay, yeah, also you have to choose a center such that it is inside of this polyhedron. You can't project it from the outside, I think. That will cause problems with
Then
convexity.
they will be in the same direction of the disk.
Sorry.
Then it will form no antipodes, I guess.
Hmm. Okay, anyway, so the area of the sphere is the summation over all polygons of the area of polygons, which is okay. And from what we know before, it is nothing but summation over all polygons. Okay, the polygons are nothing but the like projections of the faces of a cube onto the sphere, right? So whenever we are iterating over all polygons, we are iterating over faces itself. So this is nothing but the summation of angles of polygon minus n minus 2 times pi, where n is the number of sides of the polygon. Okay, this is from the before formula which we got. So just expanding the summation sign. Right. So okay, what is this sum?
Number of vertices times 2 pi.
Exactly. So basically, this is just the sum of all the angles of every polygon, right? And for each vertex, there are these angles associated with it. And since all the angles sum up to 360 degrees, it is nothing but 2 pi times the number of vertices. And we have this thing. Okay. So, okay, fine. I'll just break it now. Now, so what this is we are iterating over all polygons and we are adding 2 for every polygon. But the number of polygons is just the number of faces, because every face gets mapped to a polygon. So this thing is the number of faces, which is 2 times the number of faces. And okay, what is n? N is the number of sides of the polygon, but then it's just the projection of an edge, right? And by definition, an edge is part of 2 faces. So when we add up uh, all the across all the polygons, so like pi will get counted twice from qpil and no, not that,
Two
not that.
E we should consider, I guess.
G, I think. Huh?
Two E twice the edges.
Yeah, exactly. So 2 times the edges minus 2f, because each edge gets counted twice across every polygon. So just rewriting this, we get okay. We get 2 pi times v plus f minus e. But what we have counted is nothing but the area of the sphere, which is nothing but 4 pi. So we can equate this to 4 pi and we get the result.
Because then expected to get a spherical proof.
What do you mean?
I get it. I just said that it was unexpected to have a
Yeah,
spherical.
yeah, exactly. So like, in fact, this proof was given by Legendre in his book titled Spheres. So like, no one would look for a proof of v plus f minus e equals to in a book about spheres. So it kind of got unnoticed at that time. So yeah, it is indeed very unexpected relation between spherical geometry and this. So you people got the double counting right about this and everything else. Okay, I'm assuming you'll say yes.
Yeah.
Right. So now I'll be deriving a bunch of other properties relating to like normal spherical geometry. So like in Euclidean geometry, we have a bunch of congruencies, right? So SSS congruency and SAS congruency and then ASA congruency. And that's basically it. Okay, we'll ignore RHS for now. So you have these congruencies. So we want to see what congruencies hold in spherical geometry as well. So okay, so first I'll define poles and polars. So the simple way of thinking about a poles and polars is that if I have the equator, oops, if I have the equator, then it's one second, then its pole is are the north and south poles each, right?
Can you repeat? I couldn't hear you.
Yeah, okay. So like imagine we have the equator, right? So the you can think of poles as the north and south pole of the equator. Formally speaking, it's like you consider the plane passing through A or B or the great circle, right? And then you consider the um, line perpendicular to the plane, yeah, passing through the center. The points where it meets the sphere are the poles. I repeat. So if you have a plane, if you have 2 points A and B, which define a great circle, we consider the plane A or B and consider the uh, perpendicular line from the center to the plane and let it intersect the sphere at 2 points D and C. Those are the poles of the line, the great line, plane circle, sorry. And polars are defined in the exact opposite way. If I have a point, I consider the plane perpendicular to the line joining the point and the center. The place where it meets the sphere is the polar of the point. So just a simple, you know, lemma. If I have d is the polar of d is the pole of p, then db is equal to 90 or pi by 2. This is the spherical length, so the arc length. Does anyone want to prove this? Oh, my screen died once.
You
Yeah.
said D is the pole of B.
Yeah, so d is the pole of b.
Shouldn't it be pole of AB, like you said, pole of a line?
Oh, sorry, yeah, pole of ab. My bad.
Right.
Or you can like write it equivalently. If d is a pole of L, then for all points B on L, we have BD equals 90 degrees.
And the pole is defined as the intersection of the perpendicular with the sphere, right?
With the plane passing through the circle, yes. So it's almost by definition, since angle DEB is 90 degrees, since it's perpendicular to the plane, by definition, remember when we talked about arc length, we said that the length of PQ, the spherical length, is nothing but angle POQ, right? So the spherical length BD is nothing but angle DEB, which is equal to 90 degrees, or pi by 2 of it. Right. And you can also prove its converse. So if you have 2 points DA, I mean A and B, and if you have another point D such that DA equals DB equals pi by 2, I'll write that down. Then D is the pole of AB. This should also not be too hard to see. Does anyone want to try proving this?
I can, hello,
Hello, yes.
can I try?
Yeah, sure.
So consider the plane DEA and DEB.
Okay, DEA and DEB,
Yeah.
right?
Now we have that those we can double count and get that it somehow if we consider the upper hemisphere, it divides into 4 even parts. Thus D has to be the uh, pole of AB.
What divides into 4 equal parts? Hello? What divides the hemisphere into 4 equal parts again? Okay.
Hello, I
Anyway.
am well again. Sorry, I was a bit
y-
unusual.
Oh, yeah, it's
Uh,
fine.
like the we can consider the upper hemisphere of AB. Then we get that
Okay.
the two planes are dividing it into four equal parts.
They don't have to divide into four equal parts. So one second. This is different, right? This and this is different.
Yes, yes.
Yeah. Okay, but idea of planes is what we need. So since you have angle DEA equals angle DEB, okay, fine. DOB equals 90 or pi by 2 by definition, which is what is given. Um, we have that DE is perpendicular to the plane passing through AEB. But then this is just the definition of the pole. So we have that D is the pole of AB. Right. Mm. Okay, so one last property about poles, uh, which is a useful property. So if I have 2 points AB, and if I consider the line passing through them, and if I consider their pole, oops, right. So if AB is a line and and D is a pole, okay, then the arc length, oh, yeah, you have this thing. Okay, I mean AB, sorry. Note that this angle is spherical, so it is the angle between the tangents. Okay, so basically the proof is like consider the two tangents from D onto the onto DA and DB. So the angle between these two is by definition the angle between the two circles. So note that this line, the line tangent to D, the line tangent to the circle AD and passing through D is parallel to OA. Why?
DOA is perpendicular 90 by definition, and
Right.
that is perpendicular, which is a tangent.
Yeah, exactly. So since the tangent lies on the same plane as the circle itself, and OD is perpendicular to both the tangent and OA, we have this tangent is parallel to OA, and similarly this tangent is parallel to OB. So we get that angle AOB equals spherical angle ADB, which is nothing but um, AV. Sorry. Right. Okay.
Which is level. It can be anything, sir. Not bad.
Right. Mm. Yeah. So suppose you have 3 points A, B, C, and we see the form a triangle. We define their polar triangle as follows. So we take the pole of AB, right? O- So we take the pole of AB, which is on the same side of C, right? So D is not on the same side of C with respect to AB, right? So we take the pole of AB, which is on the same side of C. So we take E, and then we take, okay, I'll just this basically. And then we take the pole of BC on the same side as A, which is F, and the pole of AC on the same side as B. So this triangle is called the polar triangle of ABC. So the triangle HFG is called the polar triangle of ABC. Oh, sorry. The polar triangle of ABC is FGH. Okay. So first important uh, thing about polar triangles is that if we have FGH is polar triangle of ABC, then ABC is the polar triangle of FGH. So they are polar triangles of each other. Can you try proving this?
Maybe then we just do reverse mapping, like FH maps to B, GH maps to A, and FG maps to C.
What kind of mapping is this like? I
Like
mean, how do you show the
we
equality?
consider them mapping the function as uh, uh, considering the polar point.
Sure, but then how does this show this?
May I try?
Huh?
May I try?
Yeah, sure.
So F is the pole of BC. Right?
Yes.
So assume that O is the center of the sphere. So BOF is 90 degrees and H is the pole of AB. So for same reason, BOH is also 90 degrees.
Right.
So you get B is the pole of FH.
Perfect.
And you do that 3 times. And
Yes, it works. Basically using the basically using these two and this thing. So like basically what his idea is that since F is the pole of BC, angle BOF is 90 degrees. And since H is the pole of BA, angle BOH is 90 degrees as well. So by this, the lemma which we proved earlier, we have that B is the pole of HF. And similarly for the other sides, you'll get that as well. Right. So we have shown that AB, if A dash B dash C dash is a polar triangle of ABC, then ABC is the polar triangle of A dash B dash C dash. So the main advantage of polar triangles is this. So if we have ABC and A dash B dash C dash are polar triangles of each other, then we have that angle A plus B dash C dash equals 180. You can take 2 minutes to prove it. Okay, I'll give the proof. So what it is, you extend segment AB and you extend segment AC and let it meet the B dash C dash at F and G. Okay. So again, so AB intersection B dash C dash is F and AC intersection B dash C dash is G. So yeah, so this is a hint. You can try for 30 seconds or something. Okay, so use this is the idea. So you have B dash G plus C dash F equals B dash C dash plus FG. Since this is just counting again double counting length B dash C dash and then you add FG. So by definition, B dash G is nothing but pi by 2. Since B dash is the pole of AC, your B dash G is pi by 2. And similarly, C dash F is pi by 2 as well. Now, FG, wait. Oh yeah, FG is nothing but angle A because B dash A is the pole of B dash C dash, right? So by the lemma we had above, so A is also the pole of F and G. So by this lemma, we have that FG is angle A and B dash C dash is just B dash C dash. So we get the result. Did you understand the proof? Right. Okay, so basically what the idea of this is that you can write angles in terms of the sides of another triangle. So this is how it helps me. So suppose I have a triangle ABC and a triangle DEF with angle with corresponding angles equal basically. Right. In Euclidean geometry, this would be similar triangles. But what does this mean in context of spherical geometry? You can assume SSS because the proof of SSS, which I know is just using trigonometry, which is not that interesting. So we can just assume SSS and SAS for now. So can you prove that these two triangles are congruent, or if the result is false?
They have congruent polar triangles.
Yeah, exactly. So if you consider the polar triangle, so these, you get that B dash C dash equals to pi minus angle A from this, which is equal to pi minus angle D, which is equal to uh, D dash E dash, where A dash B dash C dash are polar triangle of ABC and D dash E dash F dash is polar triangle of DEF. So similarly, you get all sides are equal. So you get that triangle A dash B dash C dash is congruent to triangle D dash E dash F dash by SSS, which we are assuming for now. Um, yeah, but then now we also know that the polar triangles of the polar triangle of A dash B dash C dash is ABC, right? So we also have this. And since they're congruent, we have that angle A dash equals angle D dash. It's the same idea as before. We get that BC equals pi minus angle A dash, which equals pi minus angle D dash, which equals EF. And similarly, all other sides are equal. So since all angles and all sides are equal, we have that they're congruent. So triangle ABC is congruent to triangle DEF. So basically in spherical geometry, we have AAA congruency due to this. Since all the angles are equal, we have that they're congruent. So it's AA congruency. Did you understand the proof? I'll repeat it once again if you want. Okay, I'm assuming the proof is clear. So using the same idea, you can show ASA congruency from SAS. Right,
Even
since
SAS uses the same idea, right?
yeah, you have the same idea. Because you convert angles to lengths and you know this, so they're congruent, and then you convert the lengths to angles yet again from polar, triangles. So okay, but what about AAS? In Euclidean geometry, we take it for granted that if we have these, these two angles equal and some other random side equal to another, you know, then they're congruent. But how would you prove this again for Euclidean geometry? Assuming ASA.
In Euclidean, this isn't true, I guess.
It is true.
Oh, right. Oh, right. Yeah, understood.
Yeah, so basically what you do is just this is 180 minus angle this and this, and the same angle. Right. So these both corresponding angles are equal, and the uh, inner side is also equal, so they're congruent by ASA congruency. But the same idea cannot work here since we don't have summation of angles is 180. So in fact, AA has congruency is false. But you have a variant of it. Basically, you you get uh, one second. Yeah, but this is not true, but it's very close to true. If we have that the other angles, so okay, suppose we have this, and mm, right. So if you have these things, right, this is spherical, by the way. This is not Euclidean. Okay, this does not imply that they're congruent. But if we have that angle C, uh, if you have that angle C and angle F are not supplementary, then they are congruent. So they are either congruent or angle C plus angle F is 180. Okay, so I'll just give a brief review of spherical trigonometry because why not? Uh, so basically, you have very similar theorems to Euclidean geometry. For example, in a spherical triangle, it is 90, and this is A, B, and C. Suppose this angle C, this angle A will be. You have cos C equals cos A times cos B. This is the These are the sides, by the way. Sides are just angles in spherical geometry. So you have this in uh, spherical geometry. This is the spherical Pythagoras. Right. Using this, you can prove the spherical cosine rule, which is like you can try to prove these on your own. You have to use dot products and cross products if you know what those are. This is the angle, and the rest are the lengths. You also have sine rule working, which is interesting. So sine angle A by sine A equals sine angle B by sine B, and so on, whatever the sides are. So okay, so basically that is how you show SSs and SAS is because if you have this cosine law, you can write cos C equals cos small c minus. So the value of C is uniquely determined given the lengths of the sides. So we can find the angles using sides, and so all the corresponding angles will be equal, and you would have, congruence. And congruence is nothing but angles and sides both being equal. Yeah. Anyway, so you can try to derive properties in spherical geometry. A lot of the properties hold. So, for example, you have that the medians concur in spherical geometry. Also, yeah, there are two arc midpoints. So you have to take the one on the side. So you have that these concur. Then you also have existence of in center and in circle. Basically a lot of properties which hold in Euclidean geometry also hold in spherical geometry. So you have centroid exists, in center exists, circumcenter exists, and so on. You can try to prove those facts.
Circumcenter is obvious, I guess, because 3 points are always coplanar.
Yeah. No, but the center has to lie on the circle, the sphere, right?
All right.
And the distance is different. Like the what we said.
um,
One second, just. Mhm. So basically, you have the perpendicular bisector. What? Okay, so the perpendicular bisector is a circle. It's not a line. So you get weird stuff. I mean, it's not trivial, but its proof is similar to what we do in normal Euclidean geometry. These are the perpendicular bisectors, by the way, the blue lines. And yeah, so again, circle is nothing but circle on the uh, sphere. So that is trivial, but like you have to show that circumcenter in spherical geometry exists. Yeah, so that's it for today. Anything you people did not understand or something? Okay, then shall we stop here?